Welcome to our lecture on the water-vascular system in Asteroidea. Today, we are going to explore one of the most fascinating engineering marvels in the natural world. If you have ever wondered how a seemingly simple, squishy starfish can pry open a heavily armored clam, you are in the right place. We will uncover the biological plumbing and the physics that make this possible. Let us dive in. Now that we know what we are studying, let us look at the core principle behind it. Imagine a heavy construction excavator lifting massive piles of dirt. That machine does not use traditional muscles. It uses hydraulics, pushing fluid through tubes to create immense mechanical force. A starfish, belonging to the class Asteroidea, uses the exact same engineering principle. Instead of relying on blood and heavy muscles, the starfish has a built-in hydraulic network called the water-vascular system. It pumps seawater through a series of internal plumbing pipes to extend and retract thousands of tiny structures called tube feet. This brilliant adaptation allows them to hunt with terrifying, relentless strength. Building on this idea of a biological hydraulic machine, we must first understand where this system comes from and how water enters it. The water-vascular system is a highly specialized fluid-filled network unique to echinoderms. It actually originates from the embryonic coelom, which is the main body cavity. But how does the fluid get inside? In Asteroidea, the system begins at a sieve-like plate on the upper surface of the starfish called the madreporite. This structure acts as a crucial filter for incoming seawater, ensuring that debris does not clog the delicate internal plumbing we will explore next. Now that we have filtered seawater entering the starfish, let us trace its path through the body. The filtered water travels down a hardened, calcium-reinforced tube called the stone canal. This canal empties into a circular ring canal located right in the central disc of the animal's body. From this central ring, 5 radial canals branch out, running down the entire length of each of the starfish's arms. Finally, tiny lateral canals branch off from these radial canals. This intricate branching ensures that hydraulic pressure is distributed evenly across the entire body of the starfish. Following the water through those lateral canals brings us to the actual moving parts of our hydraulic machine. At the end of each lateral canal, there are bulbous, muscular sacs called ampullae, which attach to the tube feet, also known as podia. The mechanism is beautifully simple. When the ampulla contracts, it forces fluid down into the tube foot, extending it outward. Then, when muscles in the tube foot itself contract, they push the fluid back up into the ampulla. This back and forth fluid transfer creates a powerful suction and stepping motion, allowing the starfish to move. Having discussed the anatomy step by step, let us now visualize the entire system together. On your screen, you can see a schematic of the starfish's water-vascular system. Notice the madreporite at the top, acting as the entry point. Follow the short stone canal down to the central ring canal. From there, observe how the radial canals extend down each arm. Along these radial canals, you can clearly see the numerous bulbous ampullae and their extending tube feet. This diagram perfectly illustrates how a central fluid source powers hundreds of individual hydraulic limbs simultaneously. With a clear picture of the anatomy in our minds, we must ask, why is this specific system so critical? For a starfish, the water-vascular system is its absolute lifeline. It serves as the primary means of locomotion, food capture, and even respiration. Without it, the starfish would be completely paralyzed. It relies entirely on the coordinated suction of these tube feet to overpower the strong adductor muscles of bivalve prey. Furthermore, human engineers have heavily studied these biological hydraulics to design better soft robotics. It is a masterpiece of evolutionary design that continues to inspire modern biomechanics. Understanding how crucial this system is, let us now look at the mathematics behind its incredible strength. The water-vascular system converts fluid pressure into mechanical work. The force generated by a single tube foot is governed by the formula F equals P times A. Here, F is the mechanical force in newtons. P stands for the hydrostatic pressure created when the ampulla contracts, measured in pascals. Finally, A represents the cross-sectional area of the tube foot's base in square meters. Physically, this means if the starfish squeezes its internal fluid harder, increasing the pressure P, the resulting gripping force increases proportionally. Now that we have our formula, let us apply it to a real-world scenario. Imagine a starfish trying to attach itself to a rock in a strong ocean current. We are given an internal fluid pressure of 2,000 pascals, and the cross-sectional area of the tube foot is 0.00005 square meters. We need to find the mechanical force. We choose our hydraulic force formula because it directly relates pressure and area to force. We substitute 2,000 for P and 0.00005 for A. Multiplying these yields a final answer of 0.1 newtons. While small, this is a significant gripping power for a single microscopic structure. Since we just calculated the force of a single tube foot, we must remember that a starfish has thousands of them working together. To find the total force, we use the formula F total equals N times F. In this equation, F total represents the combined pulling force of the starfish. The variable N is the total number of active tube feet engaged in the task, and F is the force generated per individual tube foot, which we just learned how to calculate. This simple linear equation shows that if the number of engaged tube feet increases, the total macroscopic force scales up proportionally, allowing the animal to overcome individual weakness through sheer numbers. Armed with our total force equation, let us look at a more aggressive hunting scenario. A starfish wraps its arms around a clam using 800 tube feet simultaneously. We are given that each foot exerts a pulling force of 0.05 newtons. We need to calculate the total combined force applied to the clam. We use our linear scaling formula because the tube feet work in parallel. We substitute 800 for N and 0.05 for F. Multiplying these together gives us a final macroscopic force of 40 newtons. This step beautifully bridges the gap between microscopic cellular action and macroscopic hunting behavior. Having calculated that massive 40 Newton force, let us put this number into a biological perspective. 40 newtons of force is roughly equivalent to lifting a 4-kilogram weight against gravity. When a starfish attacks a clam, the clam's adductor muscles initially hold the shell tightly shut. However, the starfish applies this 40-newton hydraulic pull constantly and relentlessly. Because the starfish is using fluid pressure rather than easily fatigued muscle fibers, it can maintain this pull for hours. Eventually, the clam's muscles fatigue and give out, allowing the starfish to successfully pry the shell open and consume its meal. We have covered a lot of ground today, so let us review our key takeaways. First, the water-vascular system is a brilliant evolutionary adaptation that replaces heavy muscles with a lightweight, powerful hydraulic network controlled by the madreporite and ampullae. Second, we learned that the force of a single tube foot is governed by fluid pressure and area. Finally, we saw how the starfish scales this microscopic force by using hundreds of tube feet in unison to overpower armored prey. You now understand exactly how this fascinating creature masters fluid dynamics to survive in the ocean. Great job!